Can we let people in, Raj?
Can you see that it is being live streamed?
Yes, we can. So,
Yeah.
Okay, great. Then Lindsay will let everyone in and we will soon get started.
perfect. Well,
Oh, I think I can.
like 3.
There we go. All right, let's go.
It's always great how the counter jumps down, dives down, and then getting ready for the session. Welcome back, everyone, for the 3rd and 4th week of the program. We'll wait a few seconds for more people to get in. Welcome back, week 3 of the Global Quantum Computing and Entrepreneurship program. Today, we have a great session for you about room temperature diamond-based quantum computing and Jibran and Rashid from QWorld with quantum states and operators with complex numbers. But first, I would like to congratulate you on finishing the first 2 weeks of the program. Let us go through together briefly. 1, quantum programming. You've been working very hard on QBronze. Many of you are also still working hard today to finish the 5 quizzes and complete the certificate. There were some questions about the certificate. So the deadline will be tonight in US time, 12 p.m. It might be different in your time zone. And then later on this week, QWorld will generate the certificates based on the list that is there. So no worries if you don't get the certificate right away, it will be generated before the end of the week. Then some people were asking, what happens if I don't make it in time? Can I still continue the program? The answer is yes. This is all about learning. This is about fun. So finish the QBronze as soon as you can, and you can still continue with QSilver, earn that certificate, can continue with the rest of the program and earn the final certificate. What is the rest of the program about? Quantum programming, we will continue with QSilver, taking you from complex numbers all the way, you see the gray blocks here, to Shor's algorithm, very important, combined with a talk on post-quantum cryptography. Then, second, the hardware. We talked a lot about cryogenics and about superconducting qubits, about trapped ion qubits. Can people please mute themselves? This week, we will focus more on room temperature-based technologies. We have quantum brilliance today with diamond-based quantum computing at room temperature. On Wednesday, a lecture about photonic quantum computing. Very exciting. And next week, we will go back to the low temperatures with D-Wave, a company you might all be familiar with about quantum annealing. Then the next 3 days, we will have virtual lab tours at Princeton, at INQ, at QUIX. Really looking forward to that. And we look forward to your questions in advance about that. Entrepreneurship, how to go from idea to IPO, a panel. Careers, you will have your pitch ready training on Saturday and on Monday, a career fair with many quantum companies to impress them and see where your next step will be. And then we will move to the end of this quantum training program and getting ready for the hackathon, where many interesting challenges are waiting for you from IBM, IQM, Deloitte, Strangeworks, Orca, and more. Very exciting real-world challenges. For the career fair, August 1st, you see this beautiful poster that Madalina from our team made. Many companies will be present. And before joining this, we ask you, finish QBronze, upload your resume, and join the Pitch Ready training, so you will have all the tools to give your best pitch to employers. But what you are all waiting for today is, of course, not me, but Jennifer Harding from Quantum Brilliance. Jennifer Harding is a quantum application developer at Quantum Brilliance, and she focuses on massively parallelized room temperature-based quantum accelerators. What it is, she will tell you about more very soon. Additionally, she was an IBM Qiskit advocate too, and very strong representative in the IBM Quantum Network. She works in Germany, but the company is based in both Germany and Australia. Jennifer, we are very curious what you have to tell to us. Everyone, please ask your questions on the Discord, and I will ask them to Jennifer after the talk. Very much looking forward.
Perfect. Thank you very much for the introduction. I'll just get onto showing my screen now. Is that visible to everyone?
Great.
Yeah. Okay, perfect. As mentioned, I'm Jennifer Harding. I'm a quantum application developer here at Brilliance. So the main things that I focus on are quantum computing applications in quantum chemistry, as well as quantum benchmarking. But today we'll go through both the hardware as well as some of the applications and why these are particularly interesting for diamond-based quantum computers specifically, not just any type of quantum computers. So move on to the next slide. So who are we? Obviously, we're trying to revolutionize quantum computing, but the thing that's quite special about us is that we're room temperature quantum computers using diamond. And I'll go into a little bit more detail on how that works. So what's really special about this? Well, it's room temperature, it works at room pressure, and there's no need for any kind of complex control or laser systems. So the fact that we're able to remove a lot of these additional factors, such as kind of the fridges or the massive cooling pumps, means that we're able to have very, very small quantum computers. So the current quantum computers that we have are about the size of a desktop, and these are kind of working and installed in Pawsey Supercomputing Centre in Perth, in Australia. But what the small quantum computers allow us to do is not just, have a small quantum computer for the sake of having a small quantum computer, is they allow us to do highly parallelized quantum computing. Now, one of the key points here is that when we're saying parallelized quantum computing, we're talking about having quantum advantage in each one of those machines, but running thousands of them at the same time. So we get a bit of advantage from each of those machines, or a lot of advantage from those machines, and we exploit that even further by having thousands and thousands of machines. Now, we're hoping that our systems in maybe kind of 3 to 5 years will be the size of a lunchbox, so kind of very, very small, very comparable to some of the larger graphics cards that you have out there at the moment. And again, it's quite obvious that that really allows us to run lots at one time, because if you have the fridges, the super fridges or the super pumps, then it's very, very hard to run multiple and thousands of those at the same time, unless you want to buy a small country. So at Quantum Brilliance, everything we do is focused around this high level of parallelization. And that's one thing that we really focus on in the software. And during the hardware side, we really focus on that miniaturization. The other more obvious example of why this is useful is it allows us to have edge computing use cases. So whether that's, say, used for kind of space missions, because, maintenance is also much lower, the fact that we're not relying on difficult to get gases or liquids. And it also allows us to work in situations where, say, you may not want to transmit your data through the cloud, say for high security reasons, or it might just be the case that you want everything on site so that you're in control of everything. So there are multiple reasons why you may want this, and diamond quantum computers are really one of the top leading technologies to be able to enable quantum computing at these very small sizes and at room temperature. So another thing that we also think is quite important is when I'm looking at benchmarking, is not just looking at the computational power of your quantum computer, but also looking at some of the physical and also environmental aspects. So looking at things like the size, weight, and power consumption of the machine. I've kind of seen this two ways, or I kind of see two problems when I talk to people about, characterizing quantum advantage. They're either comparing their quantum machine to, say, the biggest supercomputer out there, or they're comparing their quantum machine to their laptop. And say you're saying, wow, I get really great advantage of my super fridge versus my laptop machine, you may think, well, is that really an advantage? Or if you're comparing, say, a desktop-sized quantum computer to Fugaku in Japan, the big supercomputing center, the HPC machine there, is that really a fair comparison? If you're able to have an enormous amount of computational power in a very small box, don't you want some way of characterizing that? So that's what we do using quantum utility. And there's a lot more to this. There's a more detailed definition, which we don't have time to go into today. But we think this is really useful to consider. It's not for everyone. Some people just want the biggest and most powerful machine, in which case look at other benchmarks such as quantum volume or Q-score or something like that. But some people are very interested in saying, well, we're interested in computational density or kind of the environmental impact, quite similar to, say, the Green 500 for classical computing. So that's kind of the why of what we do. But I guess what everyone is most interested today is how this actually works. So with regards to the three main levels that we have to control the quantum computer, it's very similar to any other type of quantum computer, with the fact that obviously it's mainly controlled by the classical machine sending the instructions to the control generation devices, which kind of convert those signals into microwave and radio frequency pulses. So again, this is probably quite similar to some of the things that you've heard about these superconducting quantum computers. And then at the heart of everything, we have this diamond chip. Now, unlike the little logo that I have here, which shows what we think of classically as a diamond, these diamonds are actually very small substrates, flat substrates, which have been created using chemical vapor deposition to get a very pure diamond substrate with some carbon-13 in there. When we have this substrate, what we do is we fire a green laser, which is a nitrogen laser, at this diamond. And what it does is it displaces some of the carbon atoms and it implants some nitrogen atoms. So what we get there is similar to this bit here. So I'm just going to minimize this. It looks like this with regards to the atomic structure. And what we use for the qubits is this nitrogen here, as well as a carbon-13 atom. So after we kind of do that bombardment and after we do the implantation of those nitrogen atoms, what happens is we kind of scan the diamond using a confocal microscope in order to see where we have that nitrogen and that carbon kind of closely close to each other to work as two qubits. And then, so that acts as two qubits. And then when we want to have a look at can say 4 or 6 qubits, then it's the case that we need multiple of these nitrogen vacancy centers close to each other. So the nitrogen and the carbon themselves, the actual nuclei are controlled using radio frequency pulses. And in order to perform entanglement, the carbon and the nitrogen aren't able to directly talk to each other, but they use an electron from the nitrogen vacancy center, which is used as a bus to kind of provide the communication between the two devices. And again, you have similar buses when you're trying to couple multiple nitrogen vacancy centers together. With regards to what that bus is, there are multiple different options out there at the moment to what it can be. The coupling of the nitrogen vacancy centers are quite difficult, but say polaratoms are one example of what it can be. One thing that's quite nice about diamond-based quantum computers, or kind of the diamond-based qubits, and we should have a video of this, it is quite nice to do an in-person demonstration, is the fact that you can do an optical readout. So the nitrogen vacancy center actually fluoresces. So you can actually do the readout just by looking at the substrate with your eye, which is quite nice. And that's the way that we actually perform the measurements at the moment. But if it's the case that you have, by performing an optical readout, obviously not with your eye, but we have systems which can do that for us. But when you have, say, lots of nitrogen vacancy centers, which are very close together, obviously you can't do the readout because you can't see which qubit is coming from. Therefore, we use magnetic field gradients in order to be able to define which qubit is giving us the result. There's quite a lot to get through and we don't have a lot of time, so I'll just quickly skim through this and feel free to ask me questions afterwards. We naturally have quite long coherence times, around 1 millisecond, without actually putting too much effort into increasing that further. And that's just because diamonds themselves are naturally very stable. It is kind of naturally very stable substrate. I think we're all quite aware of that. And that really helps us with regards to keeping the qubits in a coherent state. It does make the gate time slightly longer because obviously it's stable, so harder to manipulate. So kind of there in the order of magnitude of microseconds. I'll just skip through this very quickly. It's very important that our nitrogen vacancy center is not ionized, because the trouble is once we get an ionized center, then it's the case that we actually lose the triplet state and we just get a doublet state. And that doesn't provide basically the pulses that would apply, because the fundamental chemistry of the system changes, means that when we try and apply a pulse, it doesn't do anything because it's not operating at the frequencies we expect them to. We use the 0 and the -1 states, and the +1 state we use to measure to make sure that we still have the nitrogen vacancy triplet state. So we'll kind of perform measurements on this +1 just to see, is it still there? And then we know that we're good for doing the rest of the calculations. Because if you shine that green laser at the diamond for too long, then what happens is it does provide the ionized state that you don't want. So sorry for going through this quickly, but like I said, I'm very happy to answer questions afterwards. So at the moment, as I said, we have a 2-qubit computer in Pawsey Supercomputing Center, which runs alongside their classical HPC machines. It's obviously works at room temperature, and that's in place working at the moment. And this is a picture of the real device. We're hoping kind of 2025 that will obviously have the much smaller device with more qubits in. So it is kind of quite exciting to see what's going to happen over the next few years. In order to ensure that we can have more qubits, one of the things that's most important is going away from that technique of shooting the laser at the diamond and actually creating more kind of sophisticated implantation techniques. This is a very difficult process, and we're working with these partners here, so the University of Ulm, Fraunhofer, and Stuttgart University, as well as BMBF and Jülich. So it's a big partnership to see how we can best manage this implantation process and have lots of nice nitrogen vacancy centers close to each other. So I'm going to quickly touch on software, considering this is my area of expertise. So a couple of the things that we think could be quite interesting for diamond-based quantum computers is quantum chemistry. And this is just because we're expecting a quantum advantage of this earlier than many of the other practical use cases. We think even 20, 30 qubits, we could start to see an advantage over classical machines. With VQEs, it also looks like it might be very important in order to be able to parallelize these, because they quickly get quite large with regards to the number of gates and your gate depth, which really means that it needs to be separated into different machines. And we can do that by separating the non-commuting Pauli terms and running those on separate machines before recombining it. So really kind of specific use cases here, but I won't go into it in too much detail. And then we also have the quantum decoder, which is our speech to text translator. So what it does is when you're doing speech to text, it may not be ideal to have that speech to text translation running in the cloud, because if anyone kind of uses cloud-based speech to text at the moment, say something like Siri or Google Translate or the transcriptions that you get on Zoom, it's very delayed, and you get that delay because obviously you're talking to the cloud and back. Whereas for some use cases, you may want a more immediate response. So by running something on the edge, that could be quite beneficial here. And the reason why quantum is really useful is because for each part of, say, the word that you're saying, there are multiple guesses of what that could be. So you have all kind of 26 letters of the alphabet, if you're using an English alphabet, and then you have kind of a probability of how likely it is that that character of your phrase is one of those letters in the alphabet. And then the next character in the phrase, again, you have another 26 options. And what this does is it creates a large tree of the number of different options which you can have of what you're saying. So it's the case that if you think of it as a tree, then it's obviously kind of you have the A, and then kind of you have 26 different options on the first go, and then kind of it increases exponentially with each time step. And the way that this is managed in classical computing is you truncate each time step. So you say only have the top most 100 likely options or something like that, and then you get rid of all of the other options. What quantum allows us to do is encoding so that we keep every single option all the way to the end of your word or phrase. And then at the end, the quantum computer decides which is the most likely option, looking through all of them rather than doing a truncation. Because one thing you might get is it may be quite a promising word at the start, but it kind of, but actually the end is kind of where you get the key parts of the phrase. And you might even notice this when you're doing predictive texting, that it's much more likely to give you an answer based on how the beginning of your message is spelt rather than the whole message or the end of the message. So kind of the first few letters you write tend to be the most important. So this is a really exciting use case, and I think especially at the edge, it's going to be exciting to see what we can achieve here. So yeah, I got to the end of my slides. As I said, I understand that I ran through this quite quickly as I'm very conscious of time, but I'm happy to answer any questions now or during the Discord, or feel free to reach out to me on LinkedIn or by my email address here. Thank you very much for all your time.
This was a very interesting presentation, Jennifer, and very interesting different perspective. Thank you very much. There are quite some questions, so let's try to go through them rapidly but thoroughly. Let's start at the basics and then go more towards applications. The very basics, you use diamond. Would it also be possible with other materials? Thinking silicon, maybe buy vacancies in silicon carbide?
I wouldn't say so, just because I think, as we all know, there are many things that you can do with diamond and you just can't replicate it with any other material. As I said, the stability of the diamond crystal itself is one of the key things that we really use here, and especially for getting that long coherence time. Yeah, I think this method, diamond, it is by far the best, but there are some other options for color vacancies, but I'm just not, that's not my area of expertise. I don't believe in them quite the same way.
Great. Then you said you have a high density of qubits. What is your number of qubits at the moment?
It's only 2 qubits at the moment that we have. It's the case that we can have multiple qubits within a substrate, but they're just not entangled with each other.
Yeah, and there are more questions about that. I will combine two questions. Nasser from Algeria asks, can you please explain how does the bus between two qubits work? And Juliana from Italy asks, is the connectivity full, each qubit directly connected with another qubit?
Yeah, at the moment we have 2 qubits, so yes, it should be
for further.
Yeah, again, when we have larger systems, there'll be a limit to how much we can have the all-to-all connectivity. We do have some numbers, but I don't think we can share those. With regards to how the bus works, it's the case that both the nuclear spins are strongly correlated to the electron spin of the nitrogen vacancy. And it's the case that you can apply microwave pulses. You apply pulses separately to the nuclear spins, and that kind of puts the nuclei in the states that you want them to be in. And then you also apply pulse to radio frequency pulse to the nuclear spins and microwave pulses to the electron spins in order to get the type of rotation that you need.
Great. Then when I don't look at you, I am reading more questions on the chat. Shoria Agrawal from US asks, what techniques do you use to minimize the gate time or increase the coherence times, if any?
Yeah, at the moment, that's not our focus as far as I'm aware, just because it doesn't really look like we need increased coherence time at the moment. We're kind of quite happy. And our main focus is looking at that entanglement between the different nitrogen vacancies.
And could you comment on the work at Technical University Delft? I think Tim Taminio had 10 qubits where they had one NV center with electron spin coupled with the nuclear spins in the carbon around. And they achieved coherence times beyond a minute, if I am not wrong.
Yeah, I do believe that. I'm not saying I doubt it. It's one thing that I think we could easily increase, but as I said, it's just not our focus. I don't know if I missed another part of your question because there was just some motorbike going past quite loudly. So
that is great. Thank you very much. There are some people saying that it was a great presentation. Congratulations.
Thank you.
Pavan asks, how can we use this remote quantum computer in application-oriented perspectives? I think you already gave some examples. What do you think your quantum accelerators will be big at compared to all other types of implementations?
Yeah, it's definitely not that level of parallelization. So we're speaking to some other people from another research group who are looking into VQEs. And they said, well, for our VQEs, we actually want 30,000 quantum computers running at the same time. Obviously,
to be lunchbox size.
Yeah, exactly. The only way that you're actually going to be able to achieve that is using diamond-based. When we're talking about kind of this text-to-speech, as I said, is something that will be needed at the edge. So I do think those are two really, really key points. And I think there are lots of use cases when we think about those two things. I mean, my specialty is chemistry, so I will say the high level of parallelization. And our software stack is specifically designed to be kind of high-performance compute-based. Many people may have seen that we've now got a new collaboration with NVIDIA. So we're really developing that further. And yeah, lots of news to come out about that soon.
Then David is curious for the timeline. When will your quantum accelerators actually work in the real world?
Yeah, now. So our 2-qubit machine is there at the moment, working at room temperature, kind of showing that proof of concept. And I think it'll be kind of every 2 or 3 years that we'll have a new generation, which will be, hopefully each one will be smaller size, but more qubits.
Juliana, a quantum computing program manager in Italy, is interested in it. She asks, do you grant free access for testing your 2-qubit systems under some agreement?
It's quite I think free access is very difficult. I mean, even paid access is quite difficult. They're quite in-demand machines, to be honest with you. But we do have an emulator. It's kind of a high-performance emulator, which looks at directly replicating what diamond hardware would look like. So it's not taking shortcuts. It's kind of a like-for-like thing. And we sometimes do collaborations with other partners for the emulator.
Great. Let's go back to the physics briefly. Could you skip back a few slides where you had the band diagram? Yes, here we go, how it works. There was a question to explain this in a bit more detail. What is the role of the band gap? There are also questions, how does the temperature play a role in diamond-based systems?
Okay, the temperature question, fun fact, we actually heat our quantum computer a little bit sometimes. It doesn't need it, but to get the best results, yeah, that's fun. So I guess I'm not sure what specifically that they want to know about this diagram. Let me just...
Can you explain it more? How does heating improve the results?
It's just more stable. It's only by a couple of degrees, and like I said, it's not necessary. We can work at room temperature, but there's a difference between our testing, say, in our perfect lab environment versus our real world testing that we do at places like Pawsey. So yeah, for our kind of perfect example, we do that, but I don't know how the heating works. So with regards to this, I guess it's just trying to show the possible states that we can have for the triplet. And I guess one of the things that it demonstrates is the fact that when we're looking at the frequencies that we get here, it's obviously, we can see it's visible light. I guess I'm not entirely sure what to focus on here, but if there's a more specific question, then I can answer it.
Yeah, it has largely been covered. Great. Then the dreams of quantum brilliance. How many qubits do you expect to have in 2025? And what are the main challenges to scale it? Antonio from Spain asks.
I think the aim is 50 qubits. The challenge is just the fabrication. So we do have a team based in Freiburg in Germany who kind of have this new technique for kind of placing the nitrogen vacancy centers specifically in particular places. Yeah, so that's the aim. See how it goes.
And the background of people in the company. Is it physicists, computer scientists, or are other people also needed?
Yeah, so definitely, obviously, physicists and computer scientists, but we've just had people join that are kind of quantum chemistry specialists who don't have a strong programming or physics background. We have a lot of roles in kind of the operational side of things as well. Yeah, pretty diverse backgrounds, to be honest with you. What we found is that you really get better candidates when you're looking for people that have the potential to learn. I mean, I know it's quite a cheesy thing to say, but rather than people that really have a strong background in quantum, because not many people do exist that have the strong background in quantum. But we're obviously attending the careers fair next week. So if kind of people are interested in learning more about what's available and what kind of specific skills we're looking for, then yeah, we'll have a good presence there to talk about that further. So definitely recruiting lots.
Great. Also many opportunities for electrical engineers, mechanical engineers, variety of backgrounds.
Yeah, definitely.
Last question. Let's go briefly back to the scaling. Sharma asks, is the problem with increasing qubits that of engineering the nitrogen vacancy centers uniformly, or is it a problem of getting the right dipolar interactions? No,
it's just the dipolar interactions are fine. It's just placing them because, you know, I keep talking about this laser. It's a very, very random process. And it's just the fact that actually putting it exactly where you need it to have the nitrogen right next to the carbon-13, it's just chance at the moment. So
what is the maximum? There are more questions. There are very good questions, but I know, Jennifer, you will join the Discord
I will
right after
do.
this lecture or soon later. So further questions will be addressed by you then. Thank you very much again for this wonderful presentation and giving us insight in this. We look forward to the career fair too. And everyone, think about ways to create the uniform placement of the NP centers. Then either you get hired by Quantum Brilliance or you start your own startup as a competitor. Thank you again, Jennifer. And now Jibran Rashid will join us for the start of QSilver. Have a great day.
Thank you for having me.
Thank you very much. Yes, Jibran, you started screen sharing. A special moment because you go from QBronze to QSilver today. Not only real valued qubits, but diving into the complex numbers. Could you test your microphone, Jibran, that it doesn't interrupt too much?
Testing. Is that okay?
I think so far, yes. We will spotlight your video. Yes, please take it away. Thank you.
Thank you very much, Malu. Hello, everyone. Welcome back to QSilver. Hopefully, everyone is done with QBronze. The quizzes, the deadline was today. So there were some comments on Discord regarding getting an extension. So I think what will we end up doing is whoever's got the quizzes done by the time we collect the names for certificates, they'll end up qualifying for the QBronze certificate. However, for the entire workshop, I think what we'll do is that the quizzes will remain online afterwards. And so even though you might not qualify for the individual QBronze certificate, you can still finish all the requirements of QBronze later on, and such that you qualify for the entire Womanium workshop. Right. So if you were delayed slightly, don't worry about it. It's still possible for you to kind of finish off the entire workshop and get the certificate for the entire thing. And with that, let's set up QSilver. So as we discussed when we started QBronze, just for the purpose of this introductory workshop, right, I will clarify that. For QBronze, the number of assignments that you had were 5. All of them were pretty much multiple choice questions, and you had unlimited attempts based on feedback that we received. So that policy has been updated for QSilver. The highest score still counts. However, you only get 3 attempts at each assignment or quiz. I believe there are 6 quizzes or assignments, out of which 2 of them are actual programming assignments. So you'll be asked to download a Jupyter notebook file, edit or provide some specific code snippets in specific areas, and then upload this updated file. It will be auto-graded. There will be some delay in the auto-grading because of queue that happens on the server, so don't expect a grade right away. So in fact, let's just kind of keep that screen up. Right, so you'll have for QSilver, again, kind of the same grading policy that of all the assignments and quizzes, you need to obtain at least 50%, more than 50% on each of the assignments, with an average score overall of greater than 70%. As I mentioned, not all of these will be MCQs, right? So in general, the questions in QSilver and the content in QSilver is a bit more challenging, especially as we go along, depending on what your prior background is. There might be some prerequisites that you might be missing. So when we start off QSilver, as compared to QBronze, the expectation was that the material was being provided from a computer science perspective in QBronze. In QSilver, the introductory material is something that might be familiar to people who've done physics before, have taken an introductory quantum physics class, but a little less familiar to CS students. Then when we move on to Shor's algorithm, which forms the bulk of QSilver, then it might flip around, right? So some strong discrete math prerequisite kind of comes in, more specifically number theory. So if you've seen those number theory results before, then you're fine. If you haven't, then some of these results might be completely new. And we won't really be able to cover all the prerequisites. We will mention kind of the key results that are used, but we won't be able to discuss all the details. And so sometimes within QSilver, you might find it a little overwhelming compared to QBronze, but stick in there. It should be fine. It's still, and we've offered QSilver multiple times as well, and people have been able to successfully complete it. And I think it's more rewarding as well, so that you get a reasonably good understanding of the killer app for scalable quantum computers, i.e. Shor's algorithm. Just to recap though, again, you've got only 3 attempts for each quizzes and programming assignments in QSilver, and the deadline for completion of these quizzes will be August 7th. All right. And what you'll see also is that there will be a couple more hands-on programming sessions during QSilver compared to QBronze. The first one will be tomorrow, led by Saba. She'll be joining us tomorrow. And with that, let's start. So, the presentation style will change also. Rather than just slide-based, there will be a bit more math. So we'll work through a bit more math rather than just individual slides. Okay. So we want to come up with a general representation of a quantum bit. So it could have unlimited attempt for QSilver instead of QBronze. A little bit afraid. So Pavan, don't be afraid. It should be fine. Historically speaking, I think 3 attempts are good enough, especially if you kind of have spent the time with the notebooks early on. Just like QBronze had a bunch of notebooks that you have to download, there are a bunch of notebooks that you should download for QSilver as well. They provide lots of good exercise and practice. There are lots of programming questions and kind of conceptual questions that help you in developing your understanding of the material. All right. And as always, you can post your questions on Discord. So that should, if you're stuck, that should help out. Okay, so we get started with a recap, actually a review of complex numbers. We won't do kind of thorough details. You'll find lots of key facts and properties summarized in the introductory notebooks in QSilver tutorials. But so we've got this representation of complex numbers via 2 real numbers. Right. So imagine you've got kind of the x-axis and the y-axis, and you say I've got this value is A. I should turn this dotted as well. And you've got the y value as B, and this makes an angle theta with the x-axis. Right. So you imagine the y-axis to be representing the complex direction, complex axis, and so that's the component in the complex direction, and the x-axis is the real direction. And so for A and B real numbers, you can express any complex number as just A plus IB, where I is your square root of -1. Right. Now, one intuition that you can have right from the beginning is what happens to a number itself when we multiply it by I itself. So imagine you took this prior number Z and multiplied it with I. Well, this will give you IA plus I square B. And I square B will be equal to -1. So this gives you IA minus B, or write it as -B plus AI. How would you write this number geometrically, or visualize this number geometrically after multiplication by I? So imagine if this was your number, complex number Z, and I've just performed multiplication by I, what has happened? Imagine just trying to draw this number in the plane that we just had. It's a rotation by pi, 90 degrees. So you can imagine kind of drawing it out right like this. Right? So something along those lines. So multiplying a number by I can be visualized as a rotation by angle pi counterclockwise. And this is exactly what we'll then generalize as well, and that will be useful moving forward, right? So this will be IZ, right? This is I square B, and this then would be the angle theta. Pi over 2, right? 90 degrees pi over 2. All right. How do we come up with a generic representation or much nicer representation, which I'm sure all of you are familiar with? We recall the Taylor expansion of sine theta and cosine theta. And cosine theta equals right, and you can then combine these together in your standard Euler notation. To get 1 minus theta square, 2 factorial plus theta 4. Changes the quadrant anti-clockwise by rotation of 90 degrees. Plus I theta minus theta cubed, 3 factorial plus theta 5, 9 factorial, and that then gives you 1 plus I theta plus I theta squared, 2 factorial plus I theta cubed over 3 factorial, and so on. And this we nicely kind of summarize as, hey, that's just the expansion for an exponential. And so you get this representation EI theta. And so a multiplication by I was the special case when theta was equal to pi over 2, as you rightly mentioned, because EI pi over 2 equals I, right? So this was this rotation by 90 degrees. In general, then, EI theta admits this interpretation as an instruction to rotate by angle theta. Oops. Right, so this is a nice way to think about it. Right? In general, any complex number then will have this representation as R EI theta, where the magnitude is given by this R, right? However, since we'll be interested in representing quantum states, we will essentially be taking R equal to 1. So that simplifies our representation whenever we are representing it for qubits. Why was the theta? Oh, so that was to get our expansion to work out, right? So there are some steps missing in kind of me writing down the algebra, which you can work out to make sure how the expansion works out to the expansion for exponential. Right. So what we want to take that and plug it back into our standard representation of a qubit. We now have the familiar psi equal to alpha 0 plus beta 1. Now alpha and beta are complex numbers rather than reals. So alpha equals a plus ib, let's say. And you can take alpha star, which is the complex conjugate, to be a minus ib, right? And so we know the inner product has to equal 1. That gives us the normalization constraint as well. So you have psi, the bra vector, equals alpha star 0 plus beta star 1. And now you can calculate this inner product as alpha star 0, 0 plus beta star 1, 1. And then you have the two cross terms that will cancel out, alpha star beta 1, 0 and alpha beta star 0. Did I miss something? That's right now. I guess that would have been an alpha beta star, and that's an alpha star beta. Oops. That's 0. That's 0. This is 1. This is 1. So we get alpha star plus beta star, and that gives us the constraint that we are familiar with. So we are using conjugate kind of because we are taking by definition the bra vector over here, which is defined as such. It's a complex conjugate transpose of the original vector. Right, so it would be the transpose only if you had real entries, but because you've got complex entries, it's going to be the complex conjugate transpose. Similarly, when we get to operators, rather than having U transpose U, which was the case in Q bronze, you have U dagger U, which we'll see soon as well. That will be conjugate transpose of the matrix rather than just transpose. And so that gives us alpha magnitude square plus beta magnitude square equals 1. Right. Now, this is fine, but for a single qubit, there is a very nice visual representation of a qubit, which we'll use, which is called the block vector representation. So let's map an arbitrary psi to block sphere. Right. So some of this might be review for you. So we take two arbitrary complex numbers, R alpha EI phi alpha, and beta equal to R beta EI phi beta. Right. We take our qubit psi. That was R alpha EI phi alpha 0 plus R beta EI phi beta 1. And now we can take phi alpha just to take a screenshot. Okay. I'll share these slides on Canvas as well. So right after the session. So hopefully taking quick screenshots shouldn't be that important. All right. So don't worry about that. Okay, taking out EI phi alpha as a common factor, we get R alpha 0 plus R beta EI phi beta minus phi alpha 1. Right, and this, if you've been hearing it thrown around, is what's been referred to as the global phase, which for all practical purpose can be dropped for convenience because it does not exhibit itself in any meaningful way in our experimental observations, right? So the output or the outcomes are independent of whatever the global phase is. How can you kind of quickly check that? Let's imagine there was a unitary U that you're applying to some state psi that maps it to some other state chi. But rather, now let's say you had some global phase in front of the state psi. So UI theta, let's say, applied psi. Right? And this you could still take as, by linearity, take the EI theta out and say, this is still U just applied to psi, which gives you EI theta. And then chi over here. Right, so the probabilities that you would obtain by kind of the way we had seen measurements by the Born rule don't really change this doesn't really change the probabilities that you would obtain for measuring each of the basis states after applying the unit 2 transformation. And so this EI theta, the global factor, can always be conveniently dropped, right? So let's go back to our representation of the state from here. Well, in this mathematical representation, it's kind of clear, right? That you are able to take this factor out kind of as a common factor from this entire state psi. Whereas, as we'll see when we come to the specific description of local phase, we've seen it already in the application of phase kickback and in Grove's algorithm, where the phase is being shifted for, you've got a quantum state in superposition, and the phase is being kind of shifted for some of, let's say just the state 1 rather than state 0. And so that's something that would correspond to kind of a local phase, right? Correct. So we have psi equal to R alpha 0 plus R beta EI phi 1, where we have set phi equal to phi beta minus phi alpha. Right. So let's choose our beta EI phi. This is one complex number, right? Let's say this complex number equals x plus iy. So that would mean then that psi can be written as R alpha 0 plus x plus iy 1. Right? Let's apply the normalization constraint. Well, that says, well, R alpha we can take to be real, right? Because we kind of took out the complex factor from that. So R alpha is real. Right? So it's not a unique choice, right? R alpha square. Right, so you've got this in response to Vineet, you've got this parameter theta that shows up as kind of this free parameter almost, right? And so you can choose it in different ways. So normalization gives us R alpha square plus magnitude of x plus iy square is 1. That means R alpha square plus x square plus y square. That's what the magnitude of x plus iy will give me, has to equal 1. Right, so that's kind of our first thing that helps us in setting up our observation. You've got now 3 parameters, R alpha, x, and y. All of them are being squared, and some of them equals 1. From our kind of algebra, different coordinates transformation days, what does this equation remind you of? Excellent, unit sphere. And so that's where we kind of start off trying to put our qubit on a unit sphere. Right, so recall kind of in spherical coordinates. In fact, let's go back to our nice, in fact, a picture that we have. Right, so you've got your unit sphere. This is your kind of parameterization in terms of angle phi and theta. And you can imagine now that, for example, let's take it blue. So if this was some state EI theta with the parameters that we just had, then this component over here could be written as R sine theta. Recall R, this will be R cosine theta prime. So actually, I will term all of these thetas theta primes for our technical concern. That will show up soon. Similarly, this component over here then can be decomposed as sine theta sine phi. And this would be sine theta prime cosine phi. So phi, not phi. Right. So these components would be nice. We'll keep coming back to it again and again. So you take these components and you say, well, then psi, so that color, z0 plus x plus iy 1, where the z component, if you recall in fact, let's just try to copy this picture. I don't think the picture would be copied. Let's see. Yeah, the picture isn't copied, apologies. And notes that I'll upload, I'll make sure this is in sync. So the component along the z direction is just cosine theta prime, right? And the x and y coordinates that we just kind of wrote down in the decomposition also can be plugged in. So this would be cosine phi sine theta prime plus I sine phi sine theta prime 1. Right. So we got something that looks slightly more complicated, but let's stick with it. This can be just rewritten as 0, take out sine theta prime as a factor, and you get sine theta prime e I phi 1. Right. Now, one observation that we can make, if when we choose psi equal to 0, for what choice of theta prime and phi do I get the state 0? And if you recall very quickly, this was a phi, this was a theta prime, that's your z, this is your x, this is your y. Right, so theta prime equals 0 and phi equals 0. What would correspond to minus 0? Right. Theta prime equals pi equals still 0. And so you took this kind of hit 0, rotated by pi to get minus 0. And here now, choice that we make is to note that not just for this case of choosing states 0 and minus 0, but for actually all the qubits, which now actually will be vectors of points on the surface of this unit sphere, you can always take kind of minus that vector, and that vector is experimentally indistinguishable for us according to quantum physics, right? You can choose it to be, that's a choice you can make, right? In this case, no. In this case, this phi is not a global phase, right? Agreed? So the global phase that we had was this theta over here, not the phi. Right, so theta isn't the global phase. Sorry, yeah, theta is the global phase, and phi over here. And note over here, what I'm representing is theta prime, not theta. And so it's this EI theta in front of the state that was kind of this global thing, whereas what I'm choosing with theta prime equal to 0 is specifically this component, this amplitude in front of the state 0. right? And with phi, I'm choosing this component over here. Now, 0 and minus 0 are going to be indistinguishable from each other. And so what we can do is to say that come up with a parameterization where rather than actually having a sphere where we represent both 0 and minus 0, it's sufficient to actually parameterize just half the sphere and still kind of make it out such that we are representing all the qubits on that sphere. And we get that by basically just noting this parameterization that we say, hey, let theta equal to 2 theta prime, where theta prime was what we were running with, so that theta prime now equals theta over 2. And we plug that back into our parameterization of the state to get cosine theta over 2 rather than theta prime, 0, plus ei phi sine theta over 2, 1. How does that help us? Well, let's now actually go to the block sphere. Note what will happen now if I take this state representation that you've written, psi equal to cosine theta over 2, 0, plus ei phi sine theta over 2, 1, is that even though in our standard kind of expectation, 0 and 1 are orthogonal states, but now in this visualization of a block sphere, it's you know the standard thing one would expect is that, hey, if this is 0, then on the opposite vector would be minus 0, but that's not what will happen now in the block sphere representation. In fact, what you can now verify is that based on this parameterization, we are getting this 0 state over here, but then for what choice of theta and phi do I get 1 over here? So rather than, so if I choose theta equal to pi, I end up getting kind of exactly the antipodal point, and I get the 1 state. And so I get kind of the 2 basis states in the z basis represented in this way. And similarly, what we can then verify by plugging in, and this is something that you'll get lots of exercise in by the notebooks as well, play around with the choices of theta and phi to see how you get transformation to the plus minus state, which are the basis states for the x basis along the x-axis, and similarly the y basis states plus I and minus I. So we get a nice geometric representation for any qubit as a point on this block sphere via parameterization by this just parameters theta and phi in it, or with also kind of this nice, sometimes annoying factor of 2 kind of. Any questions about this visualization in terms of how we are getting these 6 kind of basis states in this 3-dimensional unit sphere? I would not necessarily know anything about a spinor representation. I assume that's something coming from physics, but I would guess so. Right, so my understanding as a computer scientist is that, all right, this is the standard representation of pure qubit. So a general 2-dimensional quantum system, right? I expect that there might be additional physical distinctions in terms of a bosonic state and a fermionic state and stuff like that, but no, I'm not necessarily able to pass a comment on that. Confused how to visualize 0 and minus 0. So it's a good exercise now to see within this visualization, what would minus 0 show up as, right? And so you can kind of work your way backwards to say, all right, I know any arbitrary state is going to be represented by this parameterization in this sphere. For what choices of theta and phi do I get minus 0 now? Along the 1 vector. Okay. So if this is the representation of qubits on a unit sphere, let's talk about what happens to operators on qubits. So for example, psi 0, we already know, takes 0 to 0 and takes 1 to 1, minus 1. We know its matrix representation is this. But now you note that this minus 1 over here actually was this local phase, 100 EI pi, right? And so you can now take that local phase kind of that shows up over here as EI pi and define other gates with a smaller phase change as well, right? So you have standard gates like S, which are 100 I, and that you can verify is equal to 100 EI pi 2. Or similarly, T gate, defined as such. In fact, we can do more interesting things as well, right? We can have something that was not possible as a logic gate necessarily with Boolean transformations. So if you had the X gate, for example, sorry, you could now ask about something like square root of X. So what would be, so not just about coming up with the matrix representation for the gate, but even thinking about, well, what would it mean to have a, let's say, a quantum algorithm defined, where rather than applying just a NOT gate, you're applying the square root of a NOT gate. And this was something that's kind of useful for solving one of the last problems that we saw in Grover's algorithm as well, right? So in general now, just as EI theta was an instruction for rotation, we can now similarly think about a corresponding thing for, so you should go through the calculation for whether or not square root of X is equal to Hadamard or not, in terms of figuring out why it is or why it isn't. Right. So if EI theta for numbers was this instruction to rotate, we can have a similar representation for an operator as well. So E minus IQ theta, let's say, would be here Q will be a generator of rotations. And in fact, we'll see that then we can now have a representation of an arbitrary operator, unitary operator on a qubit as a rotation on the block sphere. Right. But let's build towards that. So if you had an arbitrary rotation, let's say, you wanted to have some vector that, let's say, is along the x-axis, and you wanted to rotate it by angle theta, you could potentially kind of break it down into lots of infinitesimally small rotations. Let's say if you're breaking into n rotations, now each of these rotations would be by an angle of theta over n. So let's say R prime, the rotation that we're implementing is identity minus I epsilon q, where q was that rotation, generator of rotation, right? So most of the time we are not doing anything, but with small epsilon, we apply the rotation q. And we apply it n number of times. So let's say R prime followed by I prime and so on and so forth, some n number of times. So this will be equal to R prime to the power n. And epsilon then is theta over n. That's the rotation that each r prime kind of applies. So r itself then can be written as limit as n approaches infinity, I minus identity minus I limit. But this then can be represented as E minus I theta Q. Now, what is this Q for 2 dimensions? This is what we'll build up next. This is, so you can write an arbitrary U in 2 dimensions for a 2-level system, rather, as U equal to E minus I theta n hat dot sigma 2. Where are these coming from? Let's kind of expand upon them. So n here will be kind of your 3-component basis vector nx, ny, and z, where sigma hat is your poly vector of sigma x, sigma y, sigma z. Right? Where do we? So this can be expanded out as cosine theta over 2 identity minus I sine theta over 2 identity. No, sorry, not identity. Nx sigma x plus ny sigma y plus nz sigma z. Right? So for a standard definition of zero minus I 0. Right. So how exactly does this work out? Let's expand it. Sorry, let's add a page. Okay, so we have E minus I theta n hat dot sigma O2. We can take the expansion of this exponential as I minus identity minus I theta over 2 n hat dot sigma. So x, y, z, sigma x, sigma y, sigma z that we just defined form a are the poly matrices. They form a basis for both the set of Hermitian operators, 2x2 Hermitian operators, along with the set of 2x2 unitary operators as well. And it's a nice basis such that all 3 of them are both unitary as well as Hermitian. Right. This will be the square over 2 total minus I. Oops. Two. Now, what is sigma? The way you can write sigma is just that it's going to sigma x along your I component, sigma y along your j component, and sigma z along your k component. And we also know an identity that's satisfied by all the poly matrices, which you should verify, that sigma x square, sigma y square, sigma z square equals identity, i.e. they have eigenvalues plus minus 1. Also, for any choice of k and l, sigma k sigma l plus sigma l sigma k will equal to delta k l identity, right? So unless k and l are the same, this will evaluate to 0. This identity is helpful because we want to now kind of simplify this expression that we had, the exponential representation over here for the arbitrary unitary. And we can note then that n dot sigma square, well, will just be this thing, right? And so you'll have these entries. But then you'll have the cross entries as well. Mx ny sigma x sigma y plus ny nx sigma y sigma x. And you kind of already note how this will be useful, because using this identity over here, you will be able to note that, hey, this stuff really cancels out. And similar thing will happen for the other cross terms as well. And so you'll have nx and z sigma x sigma z plus nz and x sigma z sigma x plus nz and y sigma z sigma y plus ny nz sigma y sigma z. Right, so the three cross-term parts kind of cancel each other out, and you get something that's just nx square plus ny square plus nz square times identity. And so you get this thing equal to just identity, because this was a unit vector as well. So that part evaluates to 1 as well. Right. So how does this help us? So this means we can go back now and use this identity to plug it back in over here. So we note all the kind of square term. Oops, I missed the. Let me edit this. I missed the square term over here. So for example, this would just evaluate to identity over here, right? Whereas over here, you can kind of break it off into the identity term and then the remaining term, and so only the remaining term will be left. And so this entire thing then can be written as E minus I theta n hat dot sigma 2 equals 1 minus theta square over 2 plus theta 4 over 4 factorial plus da, 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 da. These are the terms that will happen with identity, minus I theta minus theta cubed over 3 factorial plus theta 5 over 5 factorial. So you note something very similar to how the qubit representation was working out then happens for our operator representation as well. This entire thing then is cosine theta over 2 identity minus I sine theta over 2 n dot sigma. Right? And this then can be interpreted as an arbitrary rotation. And what do you need for rotation? Well, there are two things that you need: the axis of rotation, which will be given by this vector n, and the angle of rotation, which will be given by this angle theta. Right? So then we've got this nice representation to say an arbitrary rotation on the Bloch sphere is parametrized by just this n and theta. And we have got this nice looking representation for it as well. Right? And so again, the notebooks will lead you to a nice bunch of exercises where you work through which kind of rotation or which kind of transformation simplify out into another transformation. So the practice you want to get is, imagine you've got an arbitrary point on the Bloch sphere, and you're given some other arbitrary point on the Bloch sphere, and you say, well, all right, how do I figure out an arbitrary or a transformation that leads me from state psi to a state phi? And then the additional challenge would be, well, let's assume I only have the Hadamard gate or the X gate. Well, is there a way to combine the Hadamard gate and the X gate such that, or some sequence of those transformations, which will eventually get me from psi to phi? When exactly will they cancel out? Which part do you mean will cancel out? If you meant in the expansion over here, then it is these kind of cross terms where we are using this identity that holds for polymatrices, which is easy to verify. So these three kind of terms over here will cancel out. Okay. Now, so I want to lead you through kind of the personal exercise of plugging kind of different choices of parameters, seeing what happens. So that's kind of a personal exercise that you should work through. I'll do, in fact, one more thing that's not discussed in the notebooks, kind of constructing your state. From data. Right, so we have, recall, the qubit as well as parameterized by cosine theta over 2, 0 plus AI phi sine theta over 2, 1. And we had this nice spherical parameterization as well, right, where you can now go back and check that within this vector n hat, which is components nx, ny, nz, which form the axis of rotation over here. Well, what are these components in terms of my parameters theta and phi? Given that it's a unit sphere, the magnitude is just 1, so we note then for this qubit or point on the block sphere, right? So this component over here would be just cosine theta, but this component is also just nz, right? Similarly, as we did earlier, this component over here for nx will be sine theta cosine phi, and this parameter over here will be ny, which is equal to sine theta sine phi. Right. So you take your psi, and that can be written as this vector. Well, just rewriting it as a vector rather than the Dirac notation. And do a bunch of algebra to now rewrite these points rather than in terms of theta and phi, in terms of these components nx, ny, and nz. And at the moment, it might not seem useful in terms of I would want to do that, but I'll make my point soon. So you do a bunch of algebra to get out this other parameterization, and nx plus I and y, 1 plus nz. Right, so this is now another parameterization for your same qubit, but now rather in terms of theta and phi, in terms of your kind of axis components along x, y, and z direction, in terms of nx, ny, and z. Why is that useful? Because now, well, something that we haven't explicitly covered, but for the physicist, it's kind of your bread and butter. You can calculate this expression, right? And what is this expression interpreted as? This expression is the expected value. So I'll leave the calculation for now and just mention the interpretation of measuring state psi in the z basis. So imagine you were doing an experiment where you had lots of copies of psi handed out to you, and you kept doing the measurement, and you don't know what the state psi is. and you kept doing a computational basis measurement for your state psi, you'll get some statistics out. And now you're just interested, let's say, in an aggregate data, which is what's the expected value of all the different outcomes that you obtained. That very concisely is given by just this expression. And now again, skipping over a bunch of calculations, you can verify if you are using kind of this parameterization over here, excuse me, you'll get this thing as cosine square theta over 2 plus. So for now, we are just taking considering a pure state, right? So this was a pure state psi, and here we took the bra, so you've got kind of the expected value calculated for a pure state psi, which is given by this expression, which simplifies out to this term, which itself is just cosine theta, which is equal to n sub z. So that's the expected value of the sigma z observable on. So given a state psi, if you were to get the expected value, determine the expected value of your z measurement for the state, i.e. carry out a z measurement on the state lots of times, get the result out. What you're actually calculating is exactly the term cosine theta, which is equal to n sub z. Right. And I might be off by that. Is the 2 inside the square root? Where did I? No. Sorry, sign. So that's minus. Obviously not cosine square plus sine square. And similarly, what you can verify then is n sub, the expected value of sigma y will be exactly n sub y, which is sine theta sine phi. And the expected value of sigma x, which is will be exactly n sub x sine theta sine phi, sine cosine phi. Right. So what you've been able to do is to now have a procedure for figuring out what a given state is, assuming you have multiple copies of that state. So you take the multiple copies of the state, perform your measurements, collect your statistics about, well, what's the expected value that I'm obtaining for sigma z measurement? What's the expected value I'm getting for sigma y and sigma x? And you know from this calculation that the expected value, whatever you get, will be equal to this expression. Same for x, same for z. And so now plugging it into kind of these equations, you can kind of work your way backwards and determine theta and phi from these equations. Right? And so that then allows you to determine what was the state, unknown state that you were working with. But naturally, this would require lots of copies of the state. And for sure, for specific applications, there may be better approaches for figuring out the specific parameters of the state that you have. But this is definitely one possible way you can do it. Right. Questions? Oh, so these are not just a bunch of equations, right? So what you'll get as a measurement result is this, the statistics that you will get are this left-hand side, right? The expected value can be determined from your measurement results. You just plug them in and solve the trig equations. So for example, this for sure is easily doable, right? So if you've got n sub z, you can determine theta. So do you mean these equations? So this equation is essentially saying the expected value when you perform a measurement, a z-basis measurement on your given state psi, the expected value of that measurement result is cosine theta, which is, we also note, is equal to just n sub z. Right? And a similar criteria holds for the expected value for sigma y and sigma x. The psi, sigma xi, okay. So let's actually break out this expression a little bit more. Next page. Sorry, my iPad seems to be fixed on one slide. Let me just restart my notes. All right, we're back. I think the question. Let me make sure the order is right. And so the question, I guess, being asked is, how do we understand this expression as the expected value? So let's work through that. So note that, so let's just work with sigma z, for example, to begin with. Sigma z equals 1, 0, 0 minus 1. Note sigma z is both unitary and Hermitian. So unitary transformations are the ones that we've been talking about mostly, that are to be understood as evolution of a quantum state. In our current discussion, for a single qubit, it's a rotation on a Bloch sphere. We haven't had a chance to talk about Hermitian too much, which also play kind of which is essentially what you're using in that expected value expression. So sigma z note can also be written as 0, 0 minus 1, 1, right? Based on just the matrix representation of 0, 0 of sigma z and what we know about matrices, what are the eigenvectors and eigenvalues of sigma z? So 1 minus 1, right? And in fact, so eigenvector 0 with eigenvalue 1, eigenvector 1 with eigenvalue minus 1, right? What is Hermitian requirement? Hermitian requirement is that matrix H equals H dagger, where H dagger is equal to H conjugate transpose. We can verify that that's definitely true for sigma z. It's also true for all the other polymatrices as well. So they are Hermitian. They have real eigenvalues. They have plus 1, minus 1 eigenvalues. In fact, all Hermitian matrices have real eigenvalues. All right. They are, in fact, just plus 1, minus 1, right? So the eigenvalue can be an arbitrary real number depending on what the spectrum of that matrix is. But for specifically sigma x, sigma y, sigma z, the eigenvalues are plus 1, minus 1. So in fact, they're more specific, right? And this is something actually that we used in the operator representation that we did for rotations on a Bloch sphere as well. When we figured out that expansion, one of the identities that we used, if we go back, recall, is this identity that the polymatrix is square to identity. That in fact implies that the eigenvalues are plus 1, minus 1. It should be a quick verification for that. Check out. So when we perform a measurement, one way to do that calculation is also to say, I've been given a state psi, and I want to check what's the probability that it's in state 0 and it's state 1. So what I'm doing really is to just check its inner product with 0, right? And say, hey, what's this probability? And similarly, what's this probability for an arbitrary given state, right? But given this decomposition of sigma z, you can kind of go back in and kind of think of this, the way this probability is being calculated is essentially kind of, you got probability plus 1. So this is inner product, right? So that's not the notation for condition probability. It's more like I'm given the state psi and I'm measuring in state, I want to figure out the probability that's in state 0. That can be expressed as such as well, right? And similarly for it to be in state 1. Now, this would be the formula for average or mean, right? So if I have a function that evaluates to certain values on x, and I want to figure out what the average will be, I just kind of take all the values of the function, take the value itself as well, and that will give me the average or mean. I can apply the similar kind of idea when I've got this sigma x with this decomposition and basically figure out that when I'm computing this expression that we wrote, psi sigma z psi, you kind of take the Dirac notation, plug it in over here. So you've got 0, 0, minus 1, 1, and with psi. What do we get? We get psi 0, right? Minus psi 1, 1, and then again psi. Now do the multiplication with psi as well on the right hand side. So you get psi 0, 0 psi, minus psi 1, 1 psi. That essentially will give you just, I've forgotten the, well, no, that's fine. So that's your magnitude square plus minus, sorry, minus 1 psi square, right? So now what's this? This is the probability for finding the state psi in state 0 multiplied with plus 1 over here, right? So there's a plus sign over here. Similarly, this over here is the probability that you'll find the state psi in state 1 multiplied with a minus 1. So it's kind of like minus 1 times the probability to find it in the corresponding state eigenvector plus 1 multiplied with the probability with which we'll find it in the corresponding eigenvector. So this then becomes exactly the definition of what it means to be the expected value of the state psi on sigma z, or you can just write it as expected value of sigma z as well on state psi. So that's kind of the long answer to the earlier question about, well, what did this notation mean? Sorry. This notation over here, well, this notation over here can be expanded out by this calculation to be understood as the expected value of performing a computational basis measurement on the state psi. Right? And so you can now repeat the same calculation for sigma x, sigma y, and verify that this ends up being the expected value of the observer, of the specific observable that you have over here. Right? Any additional questions? So there's lots of algebra that we've kind of jumped over in some of the calculations that we've done today. And there's lots of intuition that you may want to build up in terms of the parameterization that we've now fixed, but now figuring out, okay, based on this parameterization, for what choices of these thetas and phis do I get a state that lives where in this representation? How does the phase affect the probability of seeing a certain eigenvalue? I don't know whether I could have a general answer for that. So if you recall the phase kickback effect, for sure, what we are doing via phase kickback is, or similar kind of techniques, is to increase the amplitude of the likelihood of the state that we want to observe, right? For sure, right? So if you are, so via phase kickback, what we were doing was to increase the likelihood of destructive interference happening for the states that we don't want or are not our measurement result or not the answer for computation, and have constructive interference of amplitude amplification happen for the states that we want as a measurement result. So for indeed, playing around with these local phase is one of the key tools that we use in quantum computation. In fact, we did exactly that in Grover's algorithm. And what we'll do tomorrow then, as a step to building towards Shor's algorithm, is to see some more introductory quantum algorithms that manipulate the phase using phase kickback effect to explicitly see the interference pattern. Yeah, I may have missed a factor, and so we can put that back in. With the mean value being negative because of this, for sure, the average value or the expected value in this case will be between +1 and -1, right? Because the eigenvalues and for the observable, for the Hermitian observable, are thought to be or understood to be the values that you will observe in each specific individual run of the experiment. And then when you are kind of doing this calculation of the expected value, you are taking kind of this weighted average with, you're saying, all right, I'll get outcome +1 with this probability, well, I'll get outcome -1 with this probability. And if there are other kind of entries as well, you do that additional calculation as well. And so you get kind of this expected value calculation via this. So I don't think I'll have time to do a review of eigenvalue and eigenstate, but I think the QBronze or QSilver notebooks should have an introductory material on the basic definition of eigenvalue and eigenstates. How do you compute them and what they mean? But there's lots more to be said about that I think should be covered in a good linear algebra course. Let me see. How graphically sin theta O2 represents the component of the vector along 0 vector, but I don't understand how phi sin theta represents the component of vector along one vector. So it's the representation in the block sphere representation, right? In the block sphere representation of an arbitrary qubit psi, we are kind of saying that one way to represent the amplitudes for 0 and 1 would be this. But perhaps I might not have a meaningful enough answer for you in terms of how to build intuition in terms of why E phi sin theta O2, apart from the calculation that we've done, represents the component along the 0 direction and the 1 direction. Right? So I don't think I have a better intuition to communicate. If someone has a better intuition, please go ahead. All right, so that's it for today. We'll stop here. Tomorrow there will be a hands-on programming session with the introductory notebooks on in QSilver, along with us starting to review some introductory quantum algorithms that will lead us to the quantum Fourier transform in our third session. Thank you. So today's session was definitely something out of my comfort zone because it's a more kind of physics-oriented notation, but the standard kind of representation of a qubit in terms of block sphere is something that you want to kind of have a nice intuition for because it's used often, and it's kind of the simplest case, right? As soon as you go to 2 qubits or more, while there exists some visualization tools, there's nothing as nice and simple as a simple block sphere for a single qubit. So you do want to play around with the tools in the QSilver notebooks. That should help you to visualize some of these parameters better in terms of, well, what if the parameter choices are this? Where exactly does the qubit lie in the block sphere? And so yeah, hopefully tomorrow's session would be more useful as well in real valued quantum computing. Abdullah, good point. I think perhaps, yes, we can introduce an introductory discussion of eigenvalues and eigenvectors in QBronze. It should be useful there. At the moment, we don't. But I do believe it's there in the mathematical preliminaries section. So there is at least a definition of eigenvalues and eigenvectors in the math preliminaries in QBronze. We just don't discuss it as a discussion topic during the sessions. Right. Thank you. Malu?
Thanks a lot, Jibran. Great session, as always, as everyone pointed out. We will stay on a couple more minutes if there are more questions in general about the rest of the program, about the certificates. The next 3 days are really exciting because we have 3 virtual lab tours in a row. Tomorrow, Princeton University, neutral atoms. Then Wednesday, IonQ, trapped ion quantum computing. Thursday, QUICS, photonic quantum computing. This will be great. I will start a thread in the Discord channel that you can already ask your questions in advance and we can compile them. And of course, keep asking questions during the sessions too. And then you will be back tomorrow right away, right, Jibran? So that will be very productive. I will keep watching the Discord a bit. And I see Amirali has a question. Do you want to unmute yourself, Amirali? For further general questions about the program and about the certificates.
Exactly. So a quick question I have for Mr. Jibran is that for the lectures that you are having right now, essentially the walkthroughs we have, are you using a certain reference book or like a certain resource that you reference for all of the like the mathematical details, something that they could also reference to when you want to learn as much of the details as we have in your sessions?
So I don't necessarily have kind of one key resource to go to, but what I'll definitely do is to provide some key reference material. So there are a couple of good textbooks out there. There are a very good set of lecture notes out there. And so I can definitely share those on Discord. I might have missed doing that earlier, but I'll do that.
Thanks so much. And probably I don't want to like spam Discord. Is there a way to like message you like in LinkedIn or email somewhere that we can essentially message you and ask you questions that are more like individualistic? Like I would have a question, not sure if other people have that question.
You're more than welcome to message me directly on Discord, I think, right? So that should be possible. But if you want to email me, I can just message me in Discord and I can share my email as well. And unfortunately, I'm not on LinkedIn. So
thank you so much.
That should change, I guess. You're welcome.
Thank you, sir. Sorry, Miss Marla, so sorry.
Yeah, thanks a lot, Amirali. Great that you are very engaged every day. Also, thanks so much, everyone, again, for the great session yesterday. So amazing to hear about all your own research in so many different directions. It was a really interesting session, and we hope to repeat it upcoming Sunday with more great talks from all of you. There is a question from Sharma P. Can we take part in the career fair even if one is not interested in jobs right now? Yes, this is possible. And we ask you to indicate when you upload your resume on Canvas. If you are interested in jobs within a year, we ask you to include that in the comments. So we can highlight some of the participants who want to be spotlighted for the companies. We can highlight you if you are interested within a year. That will be around 5 people. So to repeat, for the career fair, August 1st, finish QBronze, upload your resume, ideally today, but you can still improve it until the end of the week. So you will have the best version for the companies. And 3, attend the pitch ready session on July 30th to be prepared. Mark Carrington indeed asks, what is the procedure to participate? I just summarized, so those are the 3 requirements. And based on that, you will get a separate Zoom link. So in this case, it won't be the same Zoom link, but a separate one, and we will send it to you after you finish QBronze, have your resume, and participated on Saturday. If you really can't attend the pitch ready session on Saturday, practice your 20-second pitch yourself and uploaded it on Canvas. So we see you did, and then we are sure everyone has a great pitch for the employers. Where do I have to comment? Fish asks, so on Canvas, there is an optional module. There you can upload your resume and you can add comments. One comment is, yes, I am looking for a job in quantum computing within a year. The second comment is, yes, I want to be spotlighted as a top participant for the companies. And a few participants will be selected to give a short spotlight talk about themselves in front of everyone, the employers and the participants. The 20-second pitch is supposed to be about yourself. Who are you? What is your experience and your background in what you studied and quantum computing, and what are you interested in? Why are you a good new employee for these companies? Yes, someone asks about prior certificates to be uploaded. Please tell me when I submitted the QBronze certificate I got from last summer to Canvas. It didn't take into account and the quizzes have to be worked on. It is either or. So either you do the QBronze now, or if you have a prior certificate, you can upload it and you don't need to do the quizzes now. There are some people who have a previous certificate, but they want to do QBronze again just to practice, and that is great, of course, but your prior certificate already counts. So if you just do a few, it's fine. So either you pass it now or you show that you have passed it before. Yeah, and that can be a general QBronze certificate not related to Womanium. It can also be a similar certificate, for example, from Qubit by Qubit, from the IBM summer school, Qiskit summer school a few years ago, or last year's summer school. It can be university coursework that really has a huge overlap with this. QBronze is, of course, easiest. It has the exact contents. Qubit by Qubit, IBM works too. Great, we covered the career fair, we covered prior certificates, we covered the resume and the pitch. Keep in mind, resume ideally today, but you can improve it until the end of the week for the employers. Rash, welcome in the session too. Anything to add?
I think that one of the important things to keep in mind is that now we are entering the next phase of the program. So far, you were learning the foundations, the basics, the fundamentals. Now we are going to enter the application, the jobs, the hackathons, the career fair sessions, etc. So for all of you who have been through this, fantastic. We have got more fantastic things coming ahead. Right, Malu?
Definitely. And especially, so two more weeks of this quantum training program, more in-depth knowledge about hardware, more in-depth about the programming, and then it will become really exciting with the hackathon. 2 weeks of solving a real-world hackathon challenge posed by Deloitte, IBM, IQM, Orca, Strangeworks, all companies that you have been in touch with. And the challenges are really very exciting. There is also the opportunity to pose your own challenge, your own idea in quantum computing that you want to solve or even start a startup in. You can also join the QWorld Education Challenge. You have had many interesting sessions now on quantum programming, but QWorld is also developing hardware modules, and this is where you can contribute to. So this will be an exciting time where you can show your skills and also win great prizes, great money prizes sponsored by the companies for the greatest solutions of the challenges. How many teammates can we gather for the hackathon? Upcoming Friday, there will be the hackathon introduction. Our team will tell you about the challenges, about the procedure with indeed team members, about strategies, how to win a hackathon. The best size is around 4 people, between 2 and 6. There is the opportunity to do it by yourself, but we really encourage teamwork as these challenges are bigger than the usual challenges, which are just for a 1 weekend hackathon. So we encourage you to team up, and teams are possible between 2 and 6 people. The hackathon questions will be released upcoming Friday. Friday, there will be the introduction to the hackathon. Then on Sunday, when we have the happy hour, there will be breakout rooms so you can also talk more, network more, and find good team members. And then you can sign up your team and the challenge you want until a week later.
One of the
It
good
means that a lot more information will be released about the hackathon until the end of this week.
One of the good ways of identifying good teammates and partners is looking at their participation and engagement on platforms like Discord. It will allow you to make a good understanding about the diversity of skills as well as interest that they bring to the table.
During the hackathon, there will also be mentors from the company. They will join the Discord to help and answer questions. It means that this is also a great opportunity to interact with people from these companies directly, with experts from these companies.
Marlo, do you want to briefly list the companies so that they know what to expect?
I can list the companies, but the challenges themselves will be revealed by the hackathon team on Friday. So that will be the big reveal. What are the companies? You are familiar with many of them. One company is IBM. The other company, IQM in Europe. StrangeWorks, we had Worley talking at the very beginning of our program, the keynote. His company will also pose a very interesting challenge. Then Deloitte, you might know this consultant, very broad, but they have a strong department, Quantum Link, that focuses on quantum computing and its applications. And they will pose a very applied case where you can either do a technical challenge or a business challenge. Then there is Orca Computing, focusing on photonic quantum computing. You might, when you attended Saturday's session with the career panel, we had CEO Richard Murray. His company will pose a challenge and you can work with his colleagues to solve the challenge, having them as mentors. Yeah, and then we have the QWorld challenge. We have a Womanium challenge. Am I forgetting some? Deloitte, Orca, IBM, IQM. You see, we have many different challenges for you ready to be released on Friday.
Yes, indeed. And it is really exciting. A lot of speakers who had come and spoken during the speaking sessions and afterwards, one of the common themes of questions was how to get into those industries, how to work in those industries, and what are the kind of problems and challenges that they might be working on. And this is your opportunity to get an inside flavor of the problems, the challenges, the teams, and the applications. And nothing will give you a better understanding of it than by working on real problems by real companies, and also with help, guidance, and expertise from their experts. So that is why we created and structured the hackathon as a part of this program, to help you learn, apply, and augment the skills and knowledge that you're learning through the other sessions so far.
And it's really an opportunity to stand out, building on everything you learned so far and the upcoming 2 weeks. Will Polaris QB be there? Rina Ismailati asks. Polaris QB won't be at the hackathon, but they will be at the second career fair, August 26th. And there are a variety of SDK used in the hackathon challenges. Yes, I didn't mention the Quantinuum challenge using TCAT. So the full list, Deloitte, IBM, IQM, Orca, Strangework, Quantinuum also with a very interesting challenge. Stay tuned for Friday when they will be released.
And stay focused and keep learning, because many of the skills that you learn during the hackathon, you'll be able to apply it and showcase your skills and your learnings to the industry experts.
And we encourage you to start a team formation at any point. You have seen each other in social hours. You have seen people asking questions, helping each other. Join the voice channels on Discord to meet each other. Figure out who is in your time zone to collaborate better, or maybe you don't mind and you go across time zones. You might be working with people from your own university in this program. Get your group together to make a nice team for the hackathon. There are still 2 weeks to make the teams, and this is the start to find it. What was the name of the consulting company? Deloitte. They will be at the career fair on August 1st too. So that will be your first opportunity to interact with them. Very engaged team, really, really great collaborator. Same as for the other companies, which we are really happy with to work with and to offer their expertise to all of you.
Indeed. We have a wide spectrum of companies. There are companies that specialize in quantum computation, like Quantinuum. And then there are companies that are generalized companies like Deloitte. They provide their consulting, their expertise and services to many other companies and industries across the world. And one of those sectors happens to be in quantum computing domain. So our list of companies are as varied as our participants. So we are really glad to have such a plethora of companies coming and participating.
Wonderful. More questions we will answer the next days, and then especially on Friday in the hackathon introduction, everything will be clear and be released. Looking forward to that. Thank you, Lawrence. Thank you, Sharma. Thank you, Juliana, Shoria. Thanks, everyone. And we will see each other again tomorrow, virtual lab tour and QSilver. Have a great day or night.